I'm Dr. Richard Beaser. I'm the Medical Director of Continuing Medical Education at Joslin Diabetes Centre and Senior Strategic Advisor in Education at Joslin. I'm also an Associate Professor of Medicine at Harvard Medical School. Prior to the discovery of insulin, the treatment of diabetes was quite challenging. People might live a year or two, and during that time, they were put on very, very strict diets with limited carbohydrate. The most well known of those were developed by a physician in New Jersey, Frederick Allen, and they were called the Allen diets. And he had a whole series of diets with slightly different ratios of carbohydrates and so on. And they were essentially glorified starvation diets. But it would keep people alive for a little bit longer than just letting them eat a free diet. And yet they still withered away, lost a lot of weight, and eventually did die of ketoacidosis, particularly during the winter if they had a flu or something to upset things. So that was a very grim outlook for people with type 1 diabetes. Well, the story of the discovery of insulin is very interesting. In the autumn of 1920, actually, Frederick Banting, a young London, Ontario surgeon, had the idea of an experimental procedure to ligate the pancreatic ducts and try to isolate the internal secretions and see what he could get from that as a treatment for diabetes. He took this idea to the University of Toronto to Professor J.R.R. MacLeod. MacLeod was skeptical, but for the next summer of 1921, he gave Banting the opportunity to work in his lab while he went off for summer vacation. MacLeod also assigned Banting a young medical student, Charles Best, to work with him. Banting and Best had a number of challenges during that summer in trying to get the ducts ligated and get the secretions that they were looking for. But by the end of the summer, they were able to do it. They had a diabetic dog named Marjorie. And by the time MacLeod came back from his vacation, Banting and Best were filled with excitement and were keeping Marjorie alive with injections of this internal secretion. They repeatedly did this with other dogs, so it proved the point. And at that point, MacLeod was impressed and assigned a biochemist, J.B. Collop, to the team to develop this extract, and they worked on that subsequently. By the winter of 1921 and 1922, Banting and Best were delivering papers and talking about their experiments on pancreatic extracts. By the winter of 1922, Banting and Best were comfortable that the pancreatic extracts that they had discovered were potential treatments in humans. They were talking about them, delivering papers on them, and they had the opportunity to treat a young boy named Leonard Thompson, who presented with diabetes, type 1 diabetes, to the hospital. They used insulin in treating the diabetes of Leonard Thompson, and he survived. And they were ecstatic, and he lived for a number of years thereafter. And this really proved that this discovery could be used in human beings. Professor MacLeod, in his laboratory, worked further on extracting insulin with the goal of making it commercially available to the number of people in the world with diabetes. After the discovery of insulin and some of the initial production, insulin became more widely available by 1923. On January 23rd of 1923, Banting, Best, and Collop were awarded the American patents for insulin, which they then sold to the University of Toronto for the exorbitant price of $1. And people asked, well, why didn't you cash in on this a little bit more? It's a huge discovery. But Banting reportedly said, insulin belongs to the world, not me. And I think that attitude of saying this is a discovery for the human race, I think is an attitude that was there right from the start. Production in Toronto was ramped up, and by the latter part of 1923, they were producing 250,000 units weekly. And the price of insulin at that point dropped to 5 cents, from 5 cents to 2 cents per unit. So it was relatively inexpensive at that point. Eli Lilly began to produce insulin, and Herbst also produced insulins in Europe. So there was a wide production, and at that point, it was commercially available to people that needed it. Through the 1930s, there was more development of different kinds of insulin, but it was still all animal-based insulin. Hagedorn in 1936 added protamine to insulin to prolong the duration, trying to extend the duration so people wouldn't have to take so many injections during the day. And this was before they realized that the physiologic basal and bolus pattern was important. And that led to the development in 1946 of NPH, or neutral protamine Hagedorn insulin. In the early 1950s, 1953, Novo formulated Lenti, another formulation of that longer-acting insulin. There were others earlier on, Globin and protamine zinc insulin and so on. But the Lenti and the NPH settled out in the 1950s as the two intermediate insulins. And then the original regular insulin, that's where the name regular comes from, was used at mealtime. So that was really the development through into the 1950s. And at that point, 50s and 60s, the standard of care was the split mix, regular and NPH or Lenti before breakfast and before supper, was sort of approached the natural basal and bolus patterns and was far better than just giving one long-acting injection that was sort of the standard back in the 40s as they tried to prolong insulin actions. Other insulins were developed. Ultra Lenti, trying to last 24 hours, was developed, and it was a useful insulin for its time, but its action was very irregular from one day to the next. It just had more action, less action. The absorption was variable. So at that point, it was fairly crude by today's standards, but the split mix and variations thereof were really far better than those single long-acting insulins. As we got into the 70s, people realized that, first of all, the animal insulins didn't have the supply to address the needs of the growing population of people with diabetes. And in addition, the animal insulins had a lot of impurities in them, and those affected the immune system. They led to very irregular insulin action. Action would vary from day to day. Insulin would become antibody bound. There were local injection site issues with lipohypertrophy or atrophy at injection sites. So first came the purified animal insulins, purified pork, purified beef, which tried to get away from some of those impurities. And then with the development of the synthetic insulins, the purity became much better, and the structure became essentially identical to natural human insulin, and the action pattern and the local effects on the injection sites became much less. So once we had the human insulins in the 1980s, the ability to mimic natural patterns of insulin action and the reliability of insulin improved. Subsequently, they developed a number of other analog insulins, the very long-acting insulins, even longer insulins, the very short-acting insulins, and they're now working on other formulations, smart insulins that sense the blood sugars and vary their actions accordingly, insulins that can perhaps last a week as a basal background insulin. So we're heading for an exciting era. Ranking insulin in the list of scientific breakthroughs is a little bit challenging because there are a lot of breakthroughs that occur that are not making headlines right away, but they're building blocks for subsequent developments. So if you look at perhaps a list of Nobel Prize winners in medicine, many of the discoveries are really important, but they didn't hit the front page of the newspapers the way insulin did. But it's definitely up there. amongst one of the top discoveries, sorts of other things that made the headlines, the discovery of penicillin, x-rays, a number of things like that. And I would certainly put it in that category. Diabetes, type 1 diabetes is a fairly common disease. Type 2 diabetes, which now we use insulin for in some instances, is extremely common. So if you think back to the implications of that discovery and the life-saving and the life-enhancing effect, it really is up there amongst some of the top medical discoveries. Diabetes has seen a number of very significant developments. I think that looking chronologically after insulin, the next really big development was the development of some of the oral medications. People with type 2 diabetes weren't as sick and acutely sick as those with type 1 diabetes. So they really could hide in the shadows and not come for care because they didn't want to have to take insulin. And back in the 40s and 50s, taking insulin was difficult. But with the development of the first oral medications for type 2 diabetes, the sulfonylureas, suddenly there was a way of treating diabetes that didn't involve injections. And these people came out of the woodwork and ran to their doctors to get these new pills for diabetes. And suddenly they could control their sugars reasonably well without the need for insulin. So I think that's really a major advance. Insulins advanced through the 50s, 60s, 70s, and 80s. The purer insulins, the synthetic insulins, I think were huge advances. The development of the synthetic insulins, I think was a huge advancement, not just because they were purer and they had better action profiles, more closely mimicking natural patterns, but the supply of insulin from animals, beef and pork, were not going to be enough to supply the growing population of people with diabetes. So in reality, the development of the synthetic insulins had as much to do with a supply issue as it did with a purity and a quality issue. And I think that's another major development. The ability to do easy blood testing for diabetes, certainly the urine testing first through the early years was important. But the blood testing, I think took a leap forward. First with the finger stick blood testing on chemically in strips with chemicals on the tip of it. The blood testing was a first big step. Then we came into the era of meters, where people could use their own meters and get more accurate readings. And then I think one of the major breakthroughs has been the development of continuous glucose monitoring. I liken that to the difference between a photograph and a video. Fingerstick blood sugars are like taking a photograph. Take a couple of photographs during the course of the day, and from that you try to extrapolate what's happened over 24 hours. With continuous glucose monitoring, that's analogous to a video. You have a videotape running and you see everything that went on over 24 hours. And you get a much better impression of what the glucose patterns are. For us providers, it gives us a window into what's going on and helps us develop treatment programs for people with diabetes. But for the people with diabetes themselves, I view it as even more important. It gives them daily feedback on how their decisions have affected their diabetes. If they ate a little more and took a little more insulin, they could see if that judgment on the insulin dose was good, their sugar was still too high, or the sugar was too low. And it helped train them to be more skilled at self-adjustments of their treatment program. So I think those are major developments. And certainly insulin delivery has been a major advancement. From the old glass syringes that required boiling, people were pretty much chained to their kitchens where they could boil the syringes and get everything ready. It was a multi-step process, to the advancement to disposable syringes, which allowed people to move around more and not be wedded to the kitchen. Insulin pens made it even more convenient. And now the pens, we have smart pens, which have computer capability and help calculate doses and keep logs of what people are taking for insulin. And of course, the insulin pumps which provide constant infusion of rapid-acting insulin that mimics the basal effect. Boluses are given at meals, and now the communication between the continuous glucose monitors and the pumps allows the hybrid smart pump capability, and allows the CGM to speak to the pump, drive the basal rates, and is even one step closer to mimicking natural pancreatic action.